Hello. Today we are going to be talking about our first installment in chapter 16, identifying if something is an acid or a base. So, turns out that there are several definitions of acids and bases. One definition is the Arrhenius, which is that acids donate a proton. This is what we talked about last semester when we talked about things like HCl or HBr being acids, that they had this extra hydrogen that could turn into H plus and move around the system in the reaction. Another definition of an acid is one that you will see more in organic chemistry, but this is the Lewis definition, in that it is something that accepts electrons. And so that means that it is something that tends to be positively charged. And so that means that it is a cation. These cases, these species that are positively charged, for example, NH4 plus, the ammonium ion, these cations are missing electrons, and so they can gain electrons from another species. Now, just like with acids, there are two definitions. Actually, there are a lot more, but we are going to talk about two definitions for bases. One definition is that bases accept a proton, and then another is that bases donate electrons. The accepting a proton is the Arrhenius definition, and donating electrons is the Lewis definition. And so the one that we're going to see the most in our cases is going to be the Lewis definition of a base. And this is something like ammonia that has an extra set of lone pairs, an extra set of electrons, that those electrons can be given to another species. In our situations, an acid. Because notice how in both of these definitions, acids and bases are opposites of each other. Acids donate protons, bases accept a proton. So acids donate the proton, and bases accept that same proton. In Lewis, bases are donating electrons, acids are accepting electrons. Turns out that these are the same set of electrons that the bases donate and the acids accept. Your goal is to be able to use either definition, either Lewis or Arrhenius, to be able to identify things as an acid or a base. Okay, so we're still working on trying to figure out if it's an acid or a base. There are some strong acids that we need to know for sure. These include hydrochloric acid, hydrobromic acid, hydroionic acid, nitric acid, sulfuric acid, and perchloric acid. Please memorize these acids. These are the 6 strong acids that you should know. It is a strong acid by definition because it completely dissociates in water. So whenever we take HCl and we dissolve it into water, it breaks up into its ions. And notice, we've been talking about equilibrium a lot, so notice that this arrow is a single arrow. It means that this reaction is only going in one direction. The hydrochloric acid is only breaking up into H plus and Cl minus ions in solution. This reaction does not go in reverse. So we cannot mix H plus and Cl minus ions and expect to get HCl. Okay, for strong bases, we need to memorize these as well. These are defined as group 1 and 2 oxides and hydroxides. And what we mean by group is if we look at the periodic table, I'm gonna sketch you a little periodic table here where we've got our hydrogen up here and our helium here. Group 1 and 2 are these first 2 columns. And so these are things like calcium, barium, sodium, potassium, etc. Okay? And these can either be oxides or hydroxides. And so something like barium hydroxide, BaOH2, is a strong base. And just like strong acids, things are strong bases because they dissociate completely. So the KOH, whenever I dissolve that in water, I get a one-way arrow. I get a one-way reaction to form K plus and OH minus. Just like in the acids, the reverse reaction does not happen. I cannot mix K plus potassium ion and hydroxide ion in water and expect to get potassium hydroxide. Okay, so now that we have an understanding of strong acids and bases, we need to think about weak acids and bases. So weak acids are oxoacids that are not on the list, so things like HClO, HNO2, H3PO4, carboxylic acids. Now, I'm drawing you the structure. This R group just means other atoms. So this shape, this carbon double bonded to the oxygen, bonded to the hydroxide, this shape right here, I'm going to erase that because that's messy, is what is making this the carboxylic acid. And this hydrogen in the carboxylic acid is acidic. So this is what we call an acidic proton. That means that that hydrogen can act just like the hydrogen in this HClO and donate to a base. Another thing that is a weak acid are cations, positively charged things. I mentioned this earlier with the example of NH4+. But other things that have positive charges can behave as weak acids as well. When weak acids are dissolved in water, an equilibrium is formed. So remember with our strong acids, we talked about how HCl was dissolved into water and it created H plus Cl minus, and that there was no reverse reaction that happened. Well, weak acids are not that way. In weak acids, when we dissolve them into water, an equilibrium is formed. And so, for example, when we have HClO dissolved in water, the water acts as a base, in this case, a Lewis base, and it steals a proton from this chlorate ion. And so what we get at the end is H3O+. This is what's known as the hydronium ion. Hydronium ion and the chlorate ion. Because this is an equilibrium, we can describe this reaction with an equilibrium constant. And we give this equilibrium constant the notation of a Ka. This A stands for acid. And so notice how we have that this is the same format of the Ks that we talked about in chapter 15, where we have the concentration of the products divided by the concentration of the reactants. And for a Ka, we have to have H3O plus involved. Otherwise, it's not an acid reaction. This H3O plus, this is what makes the system an acid, makes the solution acidic. Okay, so we need to think about the same sort of thing with weak bases. The main definition of weak bases that we are going to discuss today are that weak bases are species with a lone pair of electrons on the central atom. For the most case, that these are molecules with amine groups, so an NH2. And so we can write this as an R. Remember that the R is any set of atoms combined together with a nitrogen connected to a hydrogen, with a lone pair. This lone pair is what makes this act as a base. But the other thing that can act as a base is something with a negative charge. And so something like from the example that we saw a moment ago, this ClO minus, this negative charge is basic. It means that this molecule can behave as a base. And I shouldn't say molecule. This ion can behave as a base. So when weak bases dissolve in water, they also form an equilibrium, just like acids do. This equilibrium is described by the Kb. In the creative chemist way, B stands for base. And so what happens is that in this example, the ammonia, the lone pair on the ammonia, takes a hydrogen and it creates the ammonium ion and hydroxide. And so the Kb is described by the products divided by the reactants in the same format that we've seen with Ks before. Okay, so to summarize, acids can be carboxylic acid. This hydrogen attached to this single bonded oxygen is the hydrogen that moves, that is donated when it's behaving as an acid. Cations, positively charged things, can accept electrons, thus they act as an acid. And this is the generic form of the acid equilibrium that forms. And remember that this is described by a Ka. Bases are often amines, where this lone pair can donate electrons and it can steal hydrogen or a proton from acids. Anions are negatively charged species that can donate electrons, thus acting as a base. And this is the generic reaction expression that we use for how a base forms an equilibrium with water. Remember that this is described by a Kb. Okay, so I hope that you now have a little better understanding of what is an acid and what is a base. Remember that I will be having lots of office hours to be able to help you with this. So check your announcements and your emails for more information. Thank you.